Okay, so are you ready to dive in? Because today we are taking a trip through the solar system, and we're going to be encountering some seriously massive clouds.
Yeah, we're talking interstellar gas and dust clouds here.
Huge clouds. And, you might even say that a couple million years ago we bumped into them.
Yeah, a couple of times actually. We've got two research papers here, and they really lay out how these encounters with these interstellar clouds actually affected Earth's atmosphere. I mean, really left a mark.
Yeah, no kidding. Measurable effects that we can still see today.
It's pretty amazing.
So first up, we've got this paper, and they boldly titled it Earth's Mesosphere. During possible encounters with massive interstellar clouds 2 and 7 million years ago. So
Catchy.
it is catchy. So set the scene for us. What exactly did Earth run into?
Okay, so picture this. You've got this dense cloud of gas and dust, right? Thousands of times denser than the typical space between stars.
Okay.
Okay? Now imagine our solar system just cruising through the Milky Way.
Just cruising along.
And bam! We plow right through it.
Well,
Not once, but twice.
twice. Okay.
Okay?
So this is like a cosmic car wash, but instead of getting squeaky clean, our atmosphere got like a total makeover.
That's a great way to put it. Yeah, these encounters actually squeeze the heliosphere. So that's that protective bubble that our sun creates with its solar wind.
Right.
So it's kind of like if you can imagine someone like popping Earth's cosmic bubble wrap,
Okay.
just exposing us to this direct hit of interstellar material.
Talk about a rude awakening.
Yeah.
So the paper really focuses on the mesosphere, right? Which, that's way up there.
Mm-hmm.
Even above the ozone layer that we're always hearing about. What changed up there?
Well, so think of it this way. The mesosphere is already a pretty wild place. It's home to these things called noctilucent clouds,
Okay.
which you might know as those kind of electric blue clouds that you sometimes see shimmering at twilight.
Oh, yeah.
Have you seen those?
Yeah, I've seen those. I always thought it was just pollution making pretty lights.
Right.
But they're natural.
Totally natural. But they're also super sensitive to changes in atmospheric water vapor.
Okay.
And guess what? Interstellar clouds have a lot of
What's that?
water vapor.
Water vapor. It's like these clouds were carrying a super soaker ready to just drench our upper atmosphere.
Mhm. Pretty much. The models in this research suggest that those encounters would have just supercharged these noctilucent clouds, making them bigger, denser, and pushing them down to lower latitudes than we typically see them today.
Okay, so imagine you're looking up a couple million years ago instead of a few twinkling stars. You've got these giant electric blue clouds just dominating the night sky.
Yeah.
That must have been something to see.
It would have been an incredible sight. Now, there have been some theories that these intensified clouds might have even triggered ice ages by blocking out the sun.
Whoa.
Wow.
Hold on. Did those ancient folks need to break out the parkas?
That's where this research gets really interesting. They found that while these noctilucent clouds would have been way more prominent, they wouldn't have completely blanketed the Earth. They mostly would have stayed closer to the poles, and they would have stuck to their usual seasonal cycles.
Okay, so no global freeze. That's a relief.
Hmm.
But these supersized clouds still must have had some effect on sunlight, right?
Oh, absolutely. Even a little dimming can make a difference.
Right.
They quantified the potential impact using something called radiative transfer modeling.
Okay.
And they found that those massive noctilucent clouds might have blocked up to 7% of incoming sunlight at their peak.
7%. I'd definitely
Yeah.
be reaching for a sweater.
Yeah.
But we're just scratching the surface of this interstellar shenanigans, right? What about the ozone layer? Everyone's favorite atmospheric shield.
Right. Well, that's where things take another fascinating turn. You might think that all this extra interstellar material would just rip right through our ozone. Seems intuitive, right?
Right.
But that's not quite what happened. While those interstellar clouds might have zapped some ozone in the upper atmosphere, the overall ozone column likely increased.
Increased.
Yeah.
It's like saying a hailstorm made your roof stronger.
Right?
How does that even work?
Well, it's kind of like a cosmic game of chemical dominoes. The key is in those byproducts of all that extra water vapor from the interstellar cloud.
Okay.
Specifically, compounds called hetox.
Hot talks? It sounds like something straight out of a chemistry textbook.
Right.
Give us the plain English version.
Okay, so basically these Achex compounds set off this chain reaction. They do destroy some ozone, but it's up in the mesosphere. And that breakdown actually lets more UV radiation reach the lower atmosphere where most of our ozone hangs out.
Okay.
And guess what UV radiation is great at doing?
Creating ozone.
Exactly.
Okay, I'm starting to see how this unexpected ozone increase works out.
Yeah.
But what does it actually mean for Earth, good news, bad news? Or is it just too early to tell?
Well, that's the million-dollar question, right? A little ozone boost might sound nice, But there's this really delicate balance in atmospheric chemistry.
Right.
This paper mainly focuses on the mesosphere.
Okay.
So we'd really need a much broader model to see the full picture.
Got it. So more research
On
needed.
always.
But it wasn't just water vapor in those interstellar clouds, right? The paper mentioned something about interstellar dust, too.
Oh, yeah. Imagine this like a cosmic dusting of interstellar material just raining down on Earth for thousands of years. It just adds another layer to our planet's story, don't you think?
Interstellar dust settling on Earth. It's like the universe was leaving us a little souvenir.
Right.
But besides maybe giving our ancestors a sniffle,
Right.
what did this dust actually do?
Well, for one, it might have actually helped those noctilucent clouds we talked about to form more easily.
So more dust, more of those spectacular but slightly sunlight-dimming clouds.
Exactly.
Okay, got it. Anything else this cosmic dust brought to the party?
This is where it gets really interesting.
Okay.
Remember how the heliosphere, that protective bubble around our solar system, got squeezed during these encounters?
Yeah, like someone let the air out of our cosmic tires for a bit there.
Exactly. And, the heliosphere normally helps to protect us from, among other things, cosmic rays.
Cosmic rays. Those are those high-energy particles that just zip around space, right?
Yeah.
Aren't they, like, really dangerous?
Well, they can be, but they're also just a natural part of space.
Okay.
And with this squeezed heliosphere, Earth was definitely more exposed during these encounters.
So more cosmic rays were hitting Earth. Did our ancient ancestors need to, like, invest in some lead umbrellas?
Not quite, but the paper does mention the influx of interstellar hydrogen interacting with cosmic rays
Okay.
and creating this cascade of secondary particles.
Okay.
Some of those can be harmful to life.
It's starting to see why this is a big deal.
Yeah,
And this ties into the second paper you sent, right? Something about a supernova leaving its mark.
exactly. The paper is titled Life in the Bubble: How a Nearby Supernova Left Ephemeral Footprints on the Cosmic Ray Spectrum and Indelible Imprints on Life.
Okay.
And it focuses on a supernova that occurred about 2.5 million years ago, right around the time of one of those interstellar cloud encounters.
Two major cosmic events happening around the same time. That sounds more like a cosmic pile-on. Any chance this was just a coincidence?
It's possible, but the authors of this paper, they make a really compelling case that these events were actually connected. They suggest that supernova might have been the source of the interstellar cloud that Earth passed through.
Wait, the supernova made the cloud.
Yeah.
How does a star exploding on one side of the galaxy create a giant dust cloud that ends up hitting Earth?
Well, supernovae are mind-bogglingly powerful.
Right.
They don't just explode, they throw out these massive amounts of gas and dust, which expands outward like a shell.
Okay.
So it's totally plausible that one of these supernova remnants just full of hydrogen and dust is what Earth ran into.
This deep dive just took a turn for the dramatic.
Right.
And this wasn't just any supernova. This was something called a pevitron.
Right.
That sounds intense, even for a supernova.
Pevitrons are like the rock stars of supernova. They earn their name by accelerating particles to insanely high energies, up to a petaelectron volt.
Okay.
And the researchers argue that this particular pevitron left this unique signature on the cosmic ray spectrum that we can still observe today.
So like a cosmic fingerprint.
Exactly.
Yeah, I'm seeing the pieces coming together here. So a supernova explodes, creates a giant cloud. Earth gets a face full of interstellar dust and a bombardment of cosmic rays. What does that mean for life on Earth back then? Was it just a bad hair day for early hominids or something more significant?
Well, that's where things get really, really interesting.
Okay.
This paper explores the possible impacts this 1-2 punch of cosmic events might have had on early life, especially on evolution itself.
Evolution, are we talking like X-Men origins here? Did those cosmic rays give our ancestors superintelligence?
It's more subtle than that, but potentially just as profound.
Okay.
You see, cosmic rays, especially at high energies, can actually damage DNA.
Yeah.
And damaged DNA can lead to mutations.
Okay. But I thought mutations were mostly bad. Isn't that why we avoid radiation?
You're right. Most mutations are either neutral or slightly harmful.
Okay.
But every now and then, a mutation happens to be beneficial.
Okay.
And in a world that's constantly changing, those beneficial mutations are the fuel of evolution.
So this supernova might have actually sped up evolution on Earth by messing with everyone's DNA.
It's a fascinating possibility.
It really is.
And the timing is particularly interesting here.
Okay.
2.5 million years ago is about when the genus Homo, our direct ancestors, first appeared in the fossil record.
Whoa. Are you saying the supernova might be the reason we're here today? That's a lot to process.
It's definitely food for thought.
It is.
And the paper goes even deeper, exploring how that cosmic ray flux, could have affected the climate,
Okay.
potentially creating environmental shifts that favored certain evolutionary paths.
Okay, this is one heck of a deep dive. We've got glowing clouds, ozone riddles, interstellar dust, a supernova with a really cool name, and now we're talking about the origins of humankind.
It just goes to show you everything in the cosmos is connected. Events happening light years away can have ripple effects that touch our own planet, even down to the tiniest organism.
It really makes you realize we're not just living in the universe, we're a part of it.
Yeah.
But how do we know this isn't all just speculation? Did the paper provide any actual numbers to back this up?
They did.
Okay.
They used models to estimate the cosmic ray flux from that supernova and calculated the actual radiation doses life on Earth would have experienced.
Okay, time for some hard data then.
Yeah.
What kind of numbers are we talking about? Enough to make you glow in the dark.
Their calculations show that for about 100,000 years after that supernova, the cosmic ray flux would have been much higher than what we experience today.
Much higher is vague. Give me a percentage. Double the cosmic rays? Triple?
It varies depending on how far away the supernova was.
Yeah.
They looked at two likely candidates based on what we know about star clusters. For a supernova about 70 parsecs away in the Tucana Horologium Association, the radiation dose on Earth's surface would have been about 10 times higher.
10 times. Okay, that's a lot. Now I'm starting to get nervous.
Don't panic just yet.
Okay.
Remember, life is surprisingly resilient.
Okay.
For a supernova in the Upper Centaurus Lupus subgroup, which is farther away at 140 parsecs, the dose would have been about twice as high as today.
Okay, so not exactly a walk in the park, but not an extinction level event either. But still a significant increase in radiation. Did they find any proof that this actually affected life on Earth?
Well, that's where it gets tricky.
Okay.
It's really hard to definitively link specific evolutionary events to a cosmic ray burst millions of years ago.
Right.
But there are some intriguing correlations. They point to research on viruses in Africa's Lake Tanganyika.
Viruses. So this cosmic event messed with the evolution of viruses too. Not sure that's good news for us.
Well, the research shows that around 2.5 million years ago, right when that supernova would have been blasting us with cosmic rays, the rate of virus diversification in Lake Tanganyika sped up significantly.
Diversification. So not necessarily more viruses, but more kinds of viruses.
Mhm.
I guess variety is the spice of life even for viruses. But still kind of freaky, right?
It is pretty wild to think about. It really highlights how these seemingly distant cosmic events can have these ripple effects that we're still uncovering. And speaking of uncovering things, the supernova paper actually gives us some things to look for, some testable predictions.
Okay, I love when science gets predictives.
Yeah.
What can we look for to know if this supernova theory holds water?
Well, they focused on something called the knee in the cosmic ray spectrum.
A knee, okay.
Yeah, it's basically a point where the slope of the spectrum changes at higher energies, and they argue that the knee we see today is like a remnant of that ancient supernova.
So that supernova from millions of years ago left a permanent mark on the cosmic ray spectrum, like a cosmic echo.
Exactly. And here's the even cooler part. They predict that if we look at the anisotropy of cosmic rays in the PeV range...
Hold on, anisotropy? You're going to have to break that one down for us.
Right, sorry. Anisotropy just means we're looking for the direction those high-energy cosmic rays are coming from, and their theory predicts this direction should point back to where that supernova happened.
So if we can map out where those PeV cosmic rays are coming from, we can pinpoint the location of that ancient supernova. It's like using cosmic rays to do archaeology.
Precisely. And they made an even bolder prediction that this anisotropy shouldn't change direction as we move from 100 TeV to 100 PV.
Okay.
And that's significant because that's where scientists think we transition from seeing mostly cosmic rays from our own galaxy to those from other galaxies.
Okay, so two big predictions to test. The direction of these super high energy cosmic rays points back to the supernova. And that direction stays consistent even as we look at even more powerful cosmic rays. Is anyone actively looking for this right now?
Yeah, there are actually quite a few experiments around the world that are studying high-energy cosmic rays, so it's really only a matter of time before we have enough data to either support or refute these predictions.
It makes you realize how much we're still uncovering about our universe, even about events that happened millions of years ago. But even if these predictions don't pan out, just thinking about these possibilities has been incredible.
I agree. It's a great example of how interdisciplinary research can lead to such fascinating insights. We've been talking about astronomy, atmospheric science, geology, even biology, all in one deep dive.
It really highlights how everything is connected, and who knows what other secrets are waiting to be discovered as we continue to explore. For anyone listening, the next time you look up at the night sky, remember that those stars aren't just sitting there. They're part of this dynamic, evolving story that we're all a part of.
Well said. And who knows, maybe one day we'll have even more pieces of this cosmic puzzle figured out.
I can't wait. And that wraps up our deep dive into interstellar cloud supernovae and the unexpected ways they might have shaped our world. Until next time, keep those questions coming.